Hey guys, Assalamu alaikum warahmatullah. Problem 49, chapter number 23, Gauss's law. In figure, a solid sphere of radius A equal to 2.00 centimeters is concentric with a spherical conducting shell of inner radius B equal to twice A and outer radius C equal to 2.4 times A. The sphere has a net uniform charge Q1 equal to plus 5 femtocoulomb. The shell has a net charge Q2 equal to minus Q1. What is the magnitude of the electric field at a radial distance? R equal to 0, R equal to A by 2, R equal to A, R equal to 1.5 times A, R equal to 2.3 times A, and R equal to 3.5 times A. What is the net charge on the inner and outer surfaces of the shell? Okay, so we have to find out plenty of things here. What we are given is a solid sphere, this of radius A. So this part is a solid sphere. This part is a solid sphere of radius A. Then we have a concentric spherical shell. Okay, concentric spherical shell, which is conducting. Okay, conducting spherical shell. So this part is a conducting shell with an inner radius of A and outer radius of B, inner radius B and outer radius C. We are given some data. A is 2 centimeters, B is equal to twice A, C is equal to 2.4 times A. Q1, that is charge of this sphere, solid sphere of radius A, that is 5 femtocoulombs, 10 to the power minus 15. And charge of the conducting spherical shell is minus Q1, minus times this, so minus 5 femtocoulombs. We have to find out field at various points. Okay, we have to find out field at various points. So first I'll summarize a few results from what we have done in problem number 44. Okay, problem number 44 and problem number 45. From problem number 44, let me divide it into two parts. From problem 44, we were dealing with a uniformly charged non-conducting sphere. Uniformly charged non-conducting sphere, charge Q, radius R. Okay, charge Q, radius R. Well, field inside is given by gamma Q divided by capital R cube into little r. Field inside at any point at a distance r from the center. Suppose at this point at a distance r from the center. Field is given by gamma Q divided by capital R cube into little r. Capital R being the radius. Q is the total charge of the sphere. And then field on the surface is gamma Q divided by capital R square. Okay, capital R square. You just have to use capital R instead of small r because we are finding field at the surface. So small r is equal to capital R. Then field outside is equal to gamma Q divided by R square. Field outside somewhere here at a distance of r from the center. Okay, so it behaves like a point charge located at its center for points lying outside. So field inside, field on the surface, field outside. Field on the surface you can get from both these formulae. Instead of small r, we'll write capital R, we'll get the same thing. Instead of small r, we'll write the capital R, we'll get the same thing. Which simply means function is continuous at the surface. Then in problem number 45, we dealt with a spherical shell, a uniformly charged spherical shell, which could have been a conducting sphere, because in case of a conductor, all charge will lie on the surface because of mutual repulsions. Again, charge Q, radius R. Field inside the shell is equal to 0. Uniformly charged shell is equal to 0. Field outside, again, it behaves like a point charge located at the center. So that's gamma Q divided by R square. Field at any point outside at a distance r is gamma Q divided by r square. It's just same as that of a point charge. Field on the surface, remember we talked about it. Whenever we talk of surface in case of a spherical shell, we mean that we are approaching surface from outside, not from inside. If we are approaching surface from inside, then field is 0. If we are approaching surface from outside, then instead of little r here, we'll use capital R. it will become gamma q divided by capital R square. So these are the results I need to use here. This one was from problem 44 and this one is from problem 45. This one from problem 44, which we have done a few sessions before this one. This one is from problem 45. So if you want to derive these results, you can visit these problems and go through it. Now let's come to our case. So we are given a solid sphere of radius a with some charge q1. Let me write that here. This is having charge q1 and this is having charge q2, which is minus q1. We're asked to find out field at r equal to 0, then at r equal to a by 2, and then r equal to a. Okay. So from 0 to a, from 0 to b, okay, from 0 to b, that is from the center to the inner surface of the conducting shell. Field due to the conducting shell will be 0. Shell will not contribute anything to the field within it. Remember, field inside the shell is 0. Field inside the shell is 0. So this conducting charged spherical shell will not contribute to field at any point within the shell. Here, at any point within the shell. Field will be 0 because of the conducting shell. That means up to B, up to a distance of B, the only thing that contributes to the field is this charged spherical shell. Okay, is this charged spherical, charged sphere. So what is field due to this charged sphere? We'll break down the region again into two parts, from 0 to A and then from A to B. So for any point with a distance greater than 0 but less than A, less or equal to A, less or equal to 0. That means from this point to this point, from here to here at any point, if r is greater than 0 but less or equal to a. That means we're talking about points lying inside this sphere. Now we already know this is not going to contribute anything to the field, so this is the only one. And field due to this one we already know is gamma q divided by capital R cube into little r. Instead of capital R we are having a, radius a. So field is gamma q1, its charge is q1 divided by a cube into little r. This is the field from center to the surface of this spherical of this sphere, okay, of this sphere. Now in part A we're asked to find out, so I'll jump to part A now. We're asked to find out field at r equal to 0. R equal to, that is to say, at the center. At r equal to 0, field is 0. Simple. R0, everything becomes 0. Then we're asked to find out at distance a by 2. So part B, at a distance a by 2, at r equal to a by 2, at r equal to a by 2. Now a by 2 is somewhere here, okay, somewhere here. So we use the same relation. E is equal to gamma q1 divided by a cube. Instead of r, we'll write down a by 2. One of the a's will cancel out, so we're left with E equal to gamma q1 divided by twice a cube. So let's substitute the values. Gamma electrostatic constant is 9 into 10 to the power 9 in SI system. Q1 is Q1 given. Yeah, that's 5, remember 5 femtocoulomb plus 5 femtocoulomb. So 5 into 10 to the power minus 15 divided by 2 into a. This is a square, not a cube. A square. Twice a. A is given, that is 2 centimeters. So 2 into 10 to the power minus 2 meters with this square there. So this is what we have to work out. I have already done that. E at this point comes out to be 5.63, all right, 5.63 into 10 to the power minus 2. Newton per coulomb. 5.63 into 10 to the power minus 2 Newton per coulomb. This is field at a distance a by 2 from the center. Now in part C, we're asked to find out field at r equal to a. So here, exactly here on the surface. At part C, at r equal to a. So this is the surface, so field is equal to gamma q1 divided by a square. Remember, on the surface, field is gamma q divided by capital R square. Instead of capital R, we are having a as the radius and charge is q1. So let's substitute the values. Gamma is 9 into 10 to the power 9. Q1 is 5 femtocoulomb. So 5 into 10 to the power minus 15 coulomb. A is 2 centimeters. So 2 into 10 to the power minus 2 with the square. So you just have to work this out. I have already done that. Field comes out to be 11.25. 11.25 into 10 to the power minus 2 Newton per coulomb. So this is field on the surface of the sphere. Field on the surface of the sphere. Now from that point onwards, the behavior changes. Now this region from this surface to inner surface of the shell, this part is lying outside the sphere but within the spherical shell. So spherical shell will not contribute anything to the field, and sphere will behave like a point charge located at its center, because all these points from here to here are lying outside the sphere. Okay, are lying outside the sphere. So for any point at a distance greater than a, less than b. Okay, so it's done here. At a less or equal to r, less or equal to b. So meaning this part from here to here. Now this will not contribute anything to the field. This will behave like a point charge located at its center. So field will be gamma q1 divided by r square. Field will be gamma q1 divided by r square. Now in part D, we're asked to find out field at a distance of 1.5a. It is important to note here that b, inner radius, is 2.2 times a. So I'll mention that here. B is twice a, and C is where is it? 2.4 times a. 2.4 times a. So that we know if we are dealing with points lying inside it or outside it. Okay, now part D. We're asked to find out field at 1.5 times a. Part D at r equal to 1.5 times a. Now 1.5 is clearly greater than a, 1.5 times a, but is less than twice a. So that means less than b. So we are dealing with a point lying in this region, outside sphere but inside the shell. So field will be only contributed by the sphere. So field is gamma q1 divided by 1.5 times a square, r square. So 9 into 10 to the power 9 into 5 femtocoulomb, so 5 into 10 to the power minus 15 divided by 1.5 a is 2 centimeters. Yeah, 2 into 10 to the power minus 2 with the square there. So this is what we have to work out. I have already done that. E comes out to be 5 into 10 to the power minus 2. So 5 into 10 to the power minus 2 Newton per coulomb. Newton per coulomb. Okay. Then we're asked to find out field at 2.3 times a. That means within this part. Okay, within the shell. So let's go for the shell. Let's go for the shell. Okay, now our point is lying between inner surface and outer surface of this conducting shell. Okay, inner and outer surface of the conducting shell. So somewhere here, somewhere in this region, somewhere in this region. Remember, this is a metallic shell. This is a metallic shell. So field inside is 0 at all points. Okay, field inside the metal is 0 at all the points. So for B less than R less than C, so this part, this part, within the meat of the spherical shell, within the meat of the metal, field is 0. Field is 0. So that would mean part A, E, for part E, at R equal to 2.3 times A. Now 2.3 times A, remember B was twice A, B was twice A, and C was 2.4 times A. Now this is 2.3 times A, so that's greater than B, twice A, greater than twice A, but is less than 2.4 times A. So this point is lying somewhere here, somewhere here. So field is 0, simple. Field is equal to 0. This is inside the meat of the metal, so field is 0. Field at every point inside the meat of the metal is 0. Now in the next part, we're asked to find out how the charge of the sphere, spherical shell, is distributed on its inner and outer surfaces. Now we already know that in case of metals, charge is distributed only on the surface, okay, only on the surface. So total charge of this shell is minus Q1, negative of this one. So how is this minus Q1 distributed on the inner surface and on the outer surface? Because in case of metal, charge is only on the surfaces. So this charge, part of it may be lying on the inner surface and part of it may be lying on the outer surface. It has to be either on the inner or on the outer distribution on these two surfaces. Now, let's suppose inner surface is having charge Q inner and outer surface is having charge of Q out. Sum of Q in and Q out must be equal to minus Q1 because total charge is minus Q1. So what I'll do is I have drawn a Gaussian surface within this metallic spherical shell. So this is our Gaussian surface. And I'll use Gauss' law for this. Remember, integral E dot dA is equal to Q enclosed divided by epsilon 0. Okay, Q enclosed divided by epsilon 0. Now, every part of the Gaussian surface is lying within the meat of the metal. So that would mean at every point of the Gaussian surface, field is 0. Okay, field is 0 at all these points. If field is 0 at all the points, then this integral becomes 0. And on the right hand side, Q enclosed is there. What is charge enclosed by this Gaussian surface? Charge within this Gaussian surface is this Q inner and this Q1. Q outer is lying on the outer surface, which is outside this Gaussian surface. So Q inner plus Q1. So this Q enclosed is Q in plus Q1. So this would mean this whole becomes 0. Q enclosed, that would mean simply Q enclosed is equal to 0, which means Q in is equal to minus Q1. Q in is equal to minus. It has nothing to do with the total charge of the spherical shell. Nothing. If this charge were different, some Q2, Q3, Q4, whatever, this inner surface would still have minus Q1. It has nothing to do with this total charge. We did not consider total charge of this spherical shell here. If this total spherical shell had charge of capital Q, suppose, that would not affect this one because this one does not consider this total charge. So Q inner lying on the inner surface is always equal to Q minus of this Q1, negative of this Q1, equal and opposite of what is lying inside it. Okay, equal and opposite. So Q in, charge on the inner surface is minus Q1, or Q in is equal to minus 5.00 femto coulomb. But then total charge of this spherical shell is Q1, minus Q1. That would mean all the charge of this spherical shell, conducting spherical shell, is lying on the inner surface. If all of it is lying on the inner surface, then what is on the outer surface? Nothing, because nothing remains there. So Q outer must be equal to 0. Q outer must be equal. So in this particular case, with total charge of this spherical shell equal to minus Q1, all of it lies on the inner surface, nothing goes to the outer surface, so outer surface has charge 0. But if total charge of the spherical shell were something else, say capital Q, then Q inner would still be minus Q1, would still be minus q1. In that case, q out plus q in is equal to this capital Q. Then you could have found q out is equal to capital Q minus q inner. Okay, but in this case total charge is minus q1, so all of it is lying on the inner surface. Outer surface gets no shear, so charge on the outer surface is 0. Okay, that'll do for this session. Quite a long session.